We are continuing on Unit 7, Day 5, and this is the second video. So we're going to look at two examples here dealing with concavity. In the first one, we have a pretty basic cubic function, and we want to find where is this concave up or down and identify points of inflection. So the first step to doing this is always going to be to find the second derivative. So we'll find the first derivative and the second derivative. So here I get 3x squared minus 6x plus 4. And then the second derivative is 6x minus 6. So I have my two derivatives, and if we were looking at the second derivative, this is where we're going to find our potential points of inflection. So it's a little bit longer to write out than CN for critical numbers. Potential points of inflection, and I know this kind of looks like points of intersection. We're using POI for something very different than what we had normally used it for, but I will know what you mean as long as you know what you mean. So the same kind of format again as what we did for the critical numbers. The first derivative equals 0. So I'll have 6x minus 6 equals 0, 6x equals 6, x equals 1. It's a messy 6. Okay. And no values because I just have a nice linear function for my second derivative. So that obviously will exist everywhere. Now I'm going to double check whether this function changes concavity at the point x equals 1. So we will set up a table, and I'm going to look at the interval negative infinity to 1 and then 1 to infinity. And if the second derivative was like bigger and messier, you might have to do more work in your table. You might have to do a test value for something, for a second derivative that's so kind of straightforward there. I'm not going to worry too much about showing my work. If I had, say for instance, any number in this interval, so like 0, 6 times 0 minus 6 is negative. So this is just looking for the negative positive. If x is bigger than 1, then 6x minus 6 is positive. So you can do that with test values. You can do that just kind of analyzing it. You can imagine what the graph of this line looks like, whatever works, but get your signs into there. Now, when we were doing this sort of similar chart, looking at the first derivative for our intervals of increase and decrease, here I would draw arrows up or arrows down for the line where I have f at x. This is different. I'm talking about concavity, so I actually draw a little like down parabola and an up parabola to show that this is concave down and this is concave up. And this can really show you, kind of imagine, picturing sort of, I'm going to erase this after, but you've got some piece here where it's concave down and then another piece here where it's concave up. And that really starts to look like a cubic, and you know that that special point there will be your point of inflection at x equals 1. I don't want to put that in because there's actually a little bit more to this question. So when it says the point of inflection, just a kind of minor thing, the point of inflection is not x equals 1. That's the x value of the point of inflection. But when you're doing this and graphing these, I want you to actually find the full point, because we want to be able to graph this, and what the y value is at 1 really actually matters. So I'm going to just sub in f at 1. So I would have 1 minus 3 is negative 2. Plus 4 is 2, minus 5, I get negative 3. So I will say f at x is concave down from negative infinity to 1, concave up from 1 to infinity, point of inflection at 1, -3. So I do want to make sure I'm clarifying the actual full point because we want to be able to graph that. So the next question said, are there any critical numbers? So remember, critical numbers, we're dealing with the first derivative, and I'll just copy out the first derivative is 3x squared minus 6x plus 4. So thinking about, will this change sign? It's a quadratic, but what could this look like if it doesn't, if there maybe aren't any critical numbers? Can that happen in a cubic? So probably the easiest way to figure out is if we want to specify our critical numbers. Remember, we're looking at where the first derivative equals 0 and the first derivative does not exist. Now, obviously, there's no points that don't exist on a parabola, but if we use the quadratic formula, because this doesn't look like one I can factor, so x will equal 6 plus or minus the square root negative 6 squared minus 4 times 3 all over 2 times 3. So 36 minus 48. It kind of falls apart in here. When you do the quadratic formula, you don't get any solutions for critical numbers. So there's actually no points where this function will equal 0. So this derivative is never equal to 0. We know that this is a parabola opening up. So if it doesn't have any zeros, it has to be, and just kind of, if there's no zeros on this function, it has to be some kind of opening up parabola like that. So it will always be positive. So f prime at x is greater than 0 for all x. So f at x is increasing from negative infinity to infinity. I know they didn't quite ask for all of this information in the question, but if we see that the first derivative is always positive, the function is always increasing. Now, what could this look like if we have this cubic and we don't have any turning points, but we do have a point of inflection? This is a really rough graph here, guys. I apologize. We're going to have a point of inflection at 1, -3, and it's concave down before that and concave up after that. Then it kind of looks like that, and it doesn't have any turning points. So you can still find kind of an important value there that will help you with your graph, in addition to zeros and other stuff that I've probably not drawn in very accurately. But this will help you kind of show the shape of your graph. So concavity is really important. I would almost say more important when there aren't any turning points, because then you have less to guide you on your graph. The next example, I have actually given you the first and second derivative because they are really messy and terrible. Now, I've also made a video about how to use Desmos to check your work when you're doing the derivative, and it's actually a trick that I used when I was doing these big messy derivatives here, and I actually did make a mistake. So it's a good video to check out, and that will be linked in the outline as well. So here, I just want to analyze potential points of inflection. I'm not that interested on whether you can do this big, terrible derivative and not like multiply wrong like I did, and be able to get to this point. What I'm interested in is, can you analyze this and talk about where will this be positive, where will this be negative? So I'm going to list out my potential points of inflection, so here, where does the derivative not exist? The second derivative doesn't exist wherever there would be restrictions. So that would be at x equals 2 and x equals -1. And you can see, looking at the original function, those will be actually vertical asymptotes. So obviously the second derivative is not going to exist where the function has a vertical asymptote, but things might change at that vertical asymptote. You could get some interesting stuff, and you may want to know the concavity on either side of the vertical asymptote. So we're still going to check that in our table. Where does the second derivative equal 0? So I have it factored for you. It will equal 0 at x equals 1, and there's no solutions. I'm gonna not show that, but if I use a quadratic formula, there's no solutions to this quadratic. So the only potential points of inflection are where the asymptotes happen, which aren't really points of inflection, but we want to check concavity. Changes in concavity can happen there. And the potential point of inflection would be where the second derivative equals 0. We know that these ones could not be because they will be restrictions on the original function. Sometimes you could have the second derivative not exist, but it might be a point on the function. And that can happen with cubed root functions, with other kinds of rational functions that you might have, with rational exponents, that you can absolutely get kind of funny cusp shapes that could be a point of inflection, but not actually have a second derivative defined. So I'm going to set this up. I got my potential points of inflection. These critical numbers, these important numbers here, are x equals 1, x equals 2, and x equals -1. So I'm going to set up my table here from -infinity to -1, -1 to 1, 1 to 2, and 2 to infinity. So here I'm going to analyze the signs of f double prime at x. So I'm looking at, I want to come up with the sign of the derivative and interpret what that means about the graph of my function. Now in here, I'm going to do sign analysis, because I really don't like subbing a lot of numbers into a calculator. I feel like I make more mistakes with that. If you guys wanted to do, like I showed in the critical numbers video, you could just say test value and then put in the signs here. That's fine. So you might have one column here that just says test value, and you put like -2, 0, 1.5, whatever it is. But I'm not going to do that. I'm going to look at each of the factors here. So I have 1, 2, 3, 4, 5 things, which feels like a lot, but I promise it's not going to be as bad as we think. So the first one that I intentionally put in here was this -6. Sometimes people do the sign analysis, finding if things are positive or negative, and forget just like a negative constant number and have everything switch. So I always write this in, and it seems silly. -6 is negative no matter where we are. The other one, we tested this well, I did, with the quadratic formula, that's always positive. That has no zeros. So this one is always positive all the time. Okay, x minus 1. This is going to be negative if x is less than 1. So this is negative here, but then once you get a bigger number than 1, it'll be positive. Kind of the same idea, x minus 2, whatever this number is, if you cube it, it doesn't change the sign. So x minus 2 is going to be negative until you get a bigger number than 2, because if you're taking 2 away. So it's going to be negative, 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 but then here I'm bigger than 2, so it'll be positive. And x plus 1 is negative if x is before negative 1. So this would be negative. In here, if I have a number bigger than negative 1 and less than 1, if I add 1, it's going to be positive. And then these are positive numbers, so adding 1 for sure will make it positive. So that, I think, is quicker for me than testing 4 different test values on my calculator into this big mess. So I'm just going to look down and summarize. So negative, negative, positive, negative, negative. I have 4 negatives. They'll be positive. And that shows that the graph is concave up at that point. Here, negative, 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 3 negatives makes a negative. So here it's concave down. And here, negative, negative, and then positives. This will be positive. So this will be concave up. And negative, and then all these positives will be negative. So this is going to be concave down. So looking at this last summary line, you need that in there, whether you do this with test values or with the sign analysis. So remember that this one was a potential point of inflection, and these ones were asymptotes. So these cannot be points of inflection because they don't exist on the original function. But this one, at x equals 1, it does change concavity. It goes from concave down to concave up. So yes, x equals 1 is going to be a point of inflection. We're just going to test or find out what f at 1 is. So, f at 1 equals 0, which is actually kind of easy. Just looking at, if I go to sub in x equals 1, I'm going to get a 0 there. So f at 1 equals 0. So 1, 0 is a point of inflection. And it will be concave up, just to summarize, from negative infinity to negative 1 and 1 to 2. You can use this symbol, or you can just write out the and, the word and then concave down from negative 1 to 1 and 2 to infinity. So if you're not comfortable with that, the math symbol there, you can just write the word and. I've kind of done it both ways so you can see that. So you could get, say, on a test or on an assessment, if there was a bigger question, sometimes I will do that and give you the first and second derivative just to kind of save you time and make sure everybody has an accurate one, and ask you more questions just about analyzing where the critical numbers are, where the points of inflection are, where the turning points are, without having you guys do the derivatives. And sometimes on a more simple one, I would expect you to do both.